be a normal thing. Like, anyway. Yeah, so let's talk about the other of Newton's laws. So we're going to start with Newton's third. Oh, you know what? Let me go shut my door really quick. Apparently, when you have a relatively loud and deep voice, it bothers the other people that you're living with, especially if they're working too. So we're going to look at Newton's third law today, and we will also continue on. We're going to go through a lot. So we skipped 2, but we'll get there, I promise. Right, so Newton's third law is the statement for every action, there is an equal and opposite reaction. And those of you who have taken martial arts, you may have heard this before. Those of you who have read Wu books, you may have also heard this before, but this has a very precise meaning. So an action, in this case, is a force from one object on another. A reaction is a force from the second object onto the first object. I'm actually not going to write this down because I'll just be writing down what I'm saying. When we say equal, what we mean is we mean that the magnitudes of these forces are equivalent. And when we say opposite, what we mean is that because the forces are vectors, the direction of the vectors are opposite. So let me give an example. So the example here is, so I'm currently in a rolling chair. If I were to say push off with my legs against a wall, then we could analyze what types of forces there are. Or we could analyze what force made me move. So let me just finish writing out. So imagine me sticking legs out in a chair. How does one draw a rolling chair? This is the closest you'll get to me drawing anything good. So me pushing against the wall, and I'm going to and it's going to try to launch me backwards, right? So the question is what force actually made me move? So the answer here is that the only forces that can affect my motion are the forces that are acting upon me. So the force that made me move has nothing to do with my legs. I mean, it has something to do with my legs, but it's not caused by my legs. There are a few forces that affect me, but the major one here is can be determined using this force phrase. So, so one of the force phrases that would be relevant here is the, remember this business of force phrase from last time. This is the contact force on me from the wall. So the point is that I pushed on the wall. I exerted mechanical energy, I pushed on the wall, or chemical energy, I pushed on the wall. And then because of Newton's third law, we get that there is an equal and opposite force from the wall pushing back on me. So there would be a force applied this way to my legs, and then that gets carried through to everything else. Now, a question you might ask is that why didn't the wall move if I'm pushing on the wall? Well, the wall has, the wall's heavy, it has other forces holding it in place. And it's fixed to the ground, so I would have to move everything. So an example of these types of forces, the forces that are equal and opposite from Newton's third law, these are called third law force pairs. And I mean, it's just a useful name because then you can reference, you can talk about them as the same type of object. And I believe in this homework assignment, the one that I put out on Monday, I asked you to describe the third law force pairs for a particular situation. So this is what I'm talking about when I say third law force pairs. So in order to get the third law force, or the other element of the pair, if you have one element of the pair, you just swap the on and the by, or by the wall. That should be by the wall. You just swap these two. So if I wanted the force phrase for the force of me pushing on the wall, it would be the contact force on the wall by me. And those would be third law force pairs, or that would be a third law force pair. This is all just language that we're using, but the point is it illustrates that these pairs are equal and opposite. And it kind of makes sense, right? How could you push on something without it pushing back? Otherwise, there wouldn't be anything to push on, right? If I push down on a desk, there's a reason my hands don't go through the desk, and that's because the desk is pushing back up on my hands. Right, so now that we hopefully have all of the language and the intuition behind what forces are, these are things like pulling forces from tension or frictional forces or whatever, we actually can start drawing diagrams. So we're going to talk about the idea of a free body diagram, or a force diagram. You can call them either or. And these are going to be probably our essential tool for analyzing physics 9A type problems. So it's a diagram with a single object with arrows representing the force vectors drawn on it. So notice that arrows aren't actually vectors, but they represent them, right? So there are some rules for drawing a force body diagram. I'll cover those here. So it has to include only a single object. Usually we represent that object by a dot, but it doesn't have to be done. Or a block is also often used. The reason why we don't actually usually draw the shape of the object upon which we're drawing forces is that, like if it's a car, you wouldn't draw the car, is because where the force is applied doesn't matter for the free body diagram. Later, we'll talk about extended free body diagrams where you actually have to draw, the actual shape of the body upon which the forces are acting, because in that case it'll be relevant. But here it's completely irrelevant. The shape of the object doesn't matter here. Another rule is that force vectors must be real, not like real as opposed to imaginary, but real as in you have to be able to describe the force with a force phrase. So this centrifugal force that you may have heard of before, not a real force, can't describe it with a force phrase, so you wouldn't include it. So basically, make sure that any force vector you draw, you know what its force phrase is. Third rule, only forces that are actually acting on the object, I shouldn't underline forces, acting on the object are allowed. You don't want to include forces that come from the object but act on a different object. This is an important one, and one that people make that mistake quite often, where they don't do this. Though, for example, they might have included in the free body diagram for this picture here, they may have included the force of me pushing on the wall. But that's not a force on me, so it doesn't belong.
One moment.
Hopefully everybody can hear me. Oh, I can hear myself. That's confusing. One moment. All right, now I can't hear my force. Not my force, myself. Share screen. Sorry about that. I hate these sorts of things. Not like computers, but when computers crash. Go away, Office. Right? Now it's saying it has to update Office. I should have gotten a Blackboard so I could work in the event of this. I could still teach. Come on. Nobody cares, Office. All right, it's starting up. Right. All right, almost in the clear. All right, share screen. Here we go. Let me just grab the chat. Come on, one more. Manage participants. Make this just a smidge bigger. All right, so where were we? Right, we were talking about the rules for a free body force diagram. So the last thing was that only forces acting on the object are allowed. You can't have forces caused by the object on it. They have to be acting on the object. The last rule is the location of where the force is applied on the object doesn't matter. It will matter later, but for now, don't worry about it. Right. So a good example would be, let's draw the free body diagram for tug of war. The question is the question is how is it the case that either side can win if they both experience the same equal and opposite forces, right? Like if I'm tugging on the rope, then the rope is tugging on me with equal force, and similarly, and that force is caused by the other group tugging on the force. So how does either side actually move left or right if there's no actual equal and if the forces are of equal magnitude? That's a question that we can answer. So let's draw the free body diagram for a person tugging on the rope. So I'm just going to draw a circle to represent the person. Actually, I'm going to draw the picture just so you can see where all these forces come from. But again, keep in mind that usually you wouldn't actually draw a picture of what's going on. So this person, they have tension pulling on them this way. So tension on guy by other guy. That's the force phrase for that force. We have gravity acting from the center of mass downwards. That would be gravity on guy by earth. We also have a contact force pushing him upwards. This is contact on guy by ground. And then what's keeping him from being pulled along? There's friction pushing against his feet. Friction on guy by ground. And that friction it's static friction, and it's what's preventing him from moving. So how do we tell if the person wins or loses? Well, and we'll talk about this in more detail, but if the tension applied to the guy is larger than the friction applied to the guy from the ground, then he'll move to the right. Conversely, if the friction is, can you hear me? Yeah, I think you can still hear me. If the friction is of the same size as the tension, he won't move at all. So what exactly determines whether he wins or loses? Is it true that this person is at the mercy of the ground, and that that the ground decides how much friction to provide, and then whichever person the ground provides more friction to wins? Well, no, because the friction is related to the force that you can apply to the right. Precisely, Raul. When you're playing tug of war, you dig into the ground, and by doing that, you're increasing the frictional force that's applied to you, because the frictional force is an equal and opposite force pair from Newton's third law. You push on the ground forwards, and then it pushes you backwards with friction. Precisely, right. So that would be a simple example or maybe perhaps even a relatively complicated example of Newton's of force diagrams. So let's get on to Newton's second law. I can close out of this one. Right, so let's talk about Newton's second law now. So by now, we should know that we can only have accelerations if forces are present, right? That was Newton's first law. Newton's first law is that an object in motion an object at rest stays at rest unless acted upon by a force effectively. And similarly, it stays at constant velocity, meaning straight line, constant speed motion, unless there's a force. And so what are the things that acceleration does? Acceleration can either make a stationary object start moving, or it can change the velocity of an object. So we know that accelerations are only present if there are forces present on an object. So now we can analyze the forces on the objects. We can also now analyze, using these free body diagrams, what the forces on an object are. You draw all the force vectors that come off the free body diagram, add them up because they're vectors, and that's the net force acting on the object. So how do we quantify the effects of the forces on the acceleration? Well, we use the Newton's second law. The Newton's second law is basically the math equivalent of the first law. Basically, Newton thought of the concept of the first law, and then he made it formal in the second law, made it mathematically formal. So, oh, that was the second page. So we know the force isn't related to the velocity at all, because you can have a constant velocity, i.e. straight line motion with constant speed, without having any forces present. So the first law talks about changes in velocity, that is acceleration. And we know that heavy things will accelerate more slowly under the same force as light things. That's something that Newton observed and something that you guys can observe too, right? It's easier to accelerate a light weight up from the ground quickly than it is to accelerate a heavy weight up from the ground quickly, right? In fact, a weight might be so heavy that you actually can't accelerate it up enough. You can't apply enough force to counteract the acceleration applied or the force applied by gravity. So Newton concluded that acceleration is equal to the force acting on the object divided by the mass of the object. So let's check the units here. So the units of force should be equal to the units of mass times the units of acceleration, right? We know the units of mass, that's kilograms. We know the units of acceleration, it's meters per second squared. And so this should be equal to what we call newtons, abbreviated N, named after Isaac Newton, of course. So what we have here is we have a vector equation. We have the vector equation from the above, because acceleration and force are both vectors. We have A is equal to F over m. Acceleration equals force over mass. So that is to say that the acceleration, this implies that the acceleration is parallel to the force. Meaning, if you apply a force in one direction to an object, or if the net force on an object is in one direction, then it will accelerate in that direction. And one way to tell that is that the mass is always positive, so this easily checks out. So the question now is, what if there are multiple forces? Acting on an object? Because as we saw in the tug of war example, there can be multiple forces. So what we do, in order to figure out which force we use to plug into this equation, we just combine all of them. We do that using vector addition. And we use the resulting summed vector. Right, sorry, I was looking at the chat. So the composite force formed by adding up all the force vectors is called the net force. And that's the technical term that you'll hear me use a lot. And that's what fits in the equation. So what we have is we have A equals F net, the net force, divided by M, the mass of our object. So the next question you might ask is, what about where the force is applied? So as I mentioned earlier, up top, the location of where the force is applied doesn't matter as long as you discount rotation of the body. And because we're not going to be talking about rotation until near the end of the quarter, we can discount that. So instead, what we do is we apply, or how do I want to phrase this? The question might be, what is the thing that actually does the acceleration? Where can you measure the acceleration from? Because if an object's spinning, maybe one part is accelerating faster or slower than another part. So what the A actually refers to here is this is the acceleration of the center of mass. And we'll get into what the center of mass is later, but you guys should have some intuitive understanding. It's kind of like a weighted average of where all the mass is. So truly, taking this one step further, we have A sub Cm equals F net divided by M. So when we're talking about the acceleration of an object, what we're really saying is the center of mass of the object is accelerating at some particular rate. And then the rest of the stuff follows along with it, but it might also be doing other things. It might be rotating or whatever. So hopefully the force diagram at this point now makes sense. The idea is it kind of facilitates the ability to consider which forces are acting on a body and which aren't. And then you'll be able to figure out what the net force is just by adding up only the forces that are present on the force diagram. And then from there, you can actually, once you know F net, you can go and you can compute the center of mass acceleration. And most problems will basically involve you calculating the center of mass acceleration or determining some force based off of knowing what the center of mass acceleration is. So we can put all of these things together. Please don't freeze again. Oh, no, okay, it's just behaving badly. So putting Newton's laws together, is an easy task now. So let's try to answer a hypothetical or an example question. If I swing a rock on a string, sorry, it's not writing. Swing a rock on a string in a circle over my head. What happens to the rock if the string breaks? Swing a rock on a string in a circle over my, that's a lot of prepositions. if the string breaks. So this is not an obvious, there's not an obvious answer to here, or obvious answer to this problem, but if you apply what we've learned about Newton's 3 laws, you can hopefully figure this out. So maybe what we do is we would draw a free body diagram for the rock, right? And I'm just gonna draw it as part of I'm gonna draw part of the picture just so you know what I'm talking about. So what forces are acting on the rock? Actually, let me draw it slightly from a side view, so then you can see it in 3D, perhaps. So here's your rock swinging around my head. I'm holding the string, swinging it around. So there's a force on the rock pointing inwards. That's what's causing it to move in a circle, right? That's tension. There's gravity pointing downwards. Are there any other forces acting on the rock? I mean, there's air resistance, but no, there's nothing else. So what happens if the string breaks? Well, suddenly the tension force is gone, but the rocks still had some velocity. So what's going to happen is it will fly off in some direction, whatever direction it was traveling, fly off in a straight path following projectile motion. But it won't spiral at all. It'll just go straight. And this is, how a sling works, right? You swing it around and then you let go, and it just flies off straight because the string broke. You can also apply Newton's laws to understand how pulling on a spool works. Let's say that you have like a spool of thread wrapped around it, and then you just pull on it with some force. What happens to the spool? Well, it has to unwind, but which direction will it go? Well, hopefully you guys would see, and maybe this will be a good homework question or exam question even, would be that if there's only one force acting on the object, well, then it ought to move right. Now, of course, there are more complicated things going on here. Notably that there's friction involved, there's rolling involved, there's gravity, and so on. But besides that, you guys have the tools, I think, to think about this type of problem. Another example might be 2 people pushing on a wheeled cart that isn't moving, right? So let's say that you have a cart, and well, I'm not going to draw that, but there's a whole bunch of questions that you can ask. Like, if you drop a stone, what happens to the earth? Would be another example. Well, if you drop a stone, there's only one force acting on it. That would be the Earth's gravity pulling down on the rock. But every force has an equal and opposite reaction, right? That means that there's the force of gravity from the rock acting on the Earth. So the Earth moves up just a little bit. So there's a whole bunch of different applications, and you're going to see a bunch of these in the homework. But there is... oh no, my notes got all confused. But there is some more details that we should talk about. Oh no, sorry, one sec. My notes got out of order. 2. Right, okay. So I have to cover now another quantity that you may have heard in just when talking about physics from a lay perspective, or like if you've taken martial arts, these sorts of things tend to pop up a lot. There's this idea of inertia that you may have heard of. And then there's this idea of static friction. So often when people talk about inertia, what they're actually talking about is static friction. So first, let's answer the question, what is inertia? So inertia is not something to be overcome to keep something moving. So what I mean by that is, let me finish writing this. What I mean by that is that, like, if you're throwing a really heavy brick, right? It doesn't make sense to say, oh, in order to get that brick to stop, you have to overcome its inertia. That sentence doesn't make sense. Inertia is literally just mass. So what would it mean to say, oh, in order to stop that brick from moving, you have to overcome its mass? No, it's not a sensible thing to say. So really, perhaps what you're maybe thinking of is, so if something's like sliding along, let's say you have a truck, like a semi-truck whose brakes are broken. How do you, so what is the thing that stops the truck from moving? It's some sort of force, right? Forces are the only things that can accelerate, that can cause acceleration. So what I'm really getting at is the question, what resists motion if something is pushed with not enough force? Some people might say, oh, it's the inertia, but no. Right, it's precisely the static friction. It's the static friction that resists the motion. In the case of something being stationary, it's static friction. But in the case of something moving, it would be kinetic friction that is slowing it down. And that's a force that acts to slow the object down. Note that static friction is related to mass, but it's not equal to mass. So I just wanted to make sure that we cleared up this whole business of inertia versus static friction, right? Like, the reason you can't push, I don't know, the reason you can't push a 10,000 pound weight in your garage is because, or how about this? The reason you can't push a car with its brakes on is because there's a lot of static friction from between the wheels and the ground. However, if you put a 747 on an ice covered lake, you'll have a lot easier time pushing that because the static friction is minimal. So now I think we have time. Actually, you know what? That was actually all I wanted to get through today. So we can actually pause early and go over some homework questions that you guys may have had. I'll talk more about the types of forces on Monday, but why don't we do that? So then we don't have to delay, and so I can still make my meeting. So you guys had questions about the homework. So this last question involving mechanical forces, all we're talking about are just forces that are causing motion, or that could potentially cause motion. So things like pushing, things like gravity. In this case, gravity is not, gravity can cause motion, but just read this as list all of the forces, and that'll be fine. That surely is a mechanical force. Sorry about that. Right, so more questions. Normal and contact force are the same thing. Ishan, yes, you do need to know the final velocity of the rock, which is part A. Sethu, I'm not going to say it's wrong, but just make your life easier and use 10 from now on. Where do you start for question 5 on homework 2? Use Newton's second law. That's what the hint says anyway. More specifically, Newton's second law is a relationship between the acceleration and the force. Find the net force, divide it by the mass, and that gives you the acceleration. Leo, calculate, so G, if you just have the quantity G without any vector, this is just defined to be 10 meters per second squared. If you have G with a vector over it, that is 10 meters per second squared times a direction. And what direction you choose depends on your coordinate system. That's a good question, Jonathan. So force pairs are not forces that cancel out. They very specifically do not cancel out because they're acting on different objects, right? The force that so I apply a downward force to the Earth due to gravity, right? The ground applies an upwards force to me. That's a normal force. But so the normal force has an equal and opposite component, as does gravity, but they are not the same thing. So if I were to draw I'm just standing still. Let's draw the free body diagram for me. I have the force of gravity on me up, and the normal or on me down, and the force of the normal force on me up. The ground also has forces on it. It has a normal force pointing down on it, and it also has its own gravitational force pulling it down. But they're not the same thing. Like these are equal and opposite pairs, but forces are never equal and opposite pairs with something else in the same force diagram. And probably problem 1 on homework 2, should the problem say that the centripetal acceleration is towards the center of the Earth instead of away? Did I write away? I'm so sorry if I did. Yes, it should. Yeah. But I'm just looking for a magnitude, so whatever you calculate is fine. Homework number 2, does the height from where the arrow is fired matter? Is that supposed to be kept as a variable? I will leave that up to you. Calculate with it, see what happens. For number 2 on homework 2, I'm not going to give away how you find t. That's giving away the answer. For number 4 on homework 2, you don't quite understand how the rock hits the car. All right, guys, you got to slow it down. I can't answer all these that quickly. So the rock hits. So if this is your car, from the car's perspective, the rock comes in and hits it at that angle. Where this is the windshield, and this is 60 degrees. How do you find the net force vector? You add up all of the forces on the object. Only the forces on the object, and that gives you the net force vector. And all of those forces on the object are force vectors themselves, so you just add them using vector addition. Number 4, how can you determine the velocity of the rock relative to the ground? It takes a little bit of work, but use trig and use what you know about the actual motion of the rock. So a force pair is literally just so anytime you have a force from anything on anything, there will be an equal pair where you swap the from and the on, right? So if let's take, for example, I push on the wall with a force. That force, because it's due to me pushing on something, it's a contact force. So the force pair of that force that I applied is the wall pushes on me. With the same magnitude force. So force pairs are not things that you don't know that they're force pairs initially and then you link them up. Force pairs are basically, think of any force on an object, and then just you can use that to generate what its corresponding pair is. And sometimes you'll need to know what that corresponding pair is, sometimes you won't. But in general, if I'm interested in, say, what the force pair is of some force that I already know about, I just rearrange it. It's not the force. It was the force I applied to the wall. Now it's the force the wall applies to me. Same force, same magnitude, opposite, or different force, same magnitude, opposite direction. Yeah, I think that I was just thinking about how I can adjust homework 1. The problem, or homework 2 problem 1, I just need to rephrase it so it's centripetal motion away or towards the Earth. By the way, the reason why there's some confusion there is because the acceleration is towards the Earth, you weigh slightly less, so it's as if there were a centrifugal force pushing you away from the Earth. So what I was asking is, what is the equivalent acceleration of the centrifugal force that you would have had? But that's just it's just a notation thing almost. For number 5, do you need to change 5 kilograms to grams? No. So the base SI unit for mass is kilograms. We use kilograms, meters, and seconds. I'm going to send out a quick email to the grader for homework 1 to indicate to him the issue with the last problem. If there are any other errors in the answer key for homework 1, email me, and because I looked over most of it, but apparently he misunderstood what I meant when I said average velocity. This week is particularly slow because we're still getting used to how the grading exchange goes for solutions and all that. It could take, somewhere between 2 and 5 days is my guess. Usually it'll be done by the following Monday is what I would like, but I can't guarantee that. For problem 6 for the diagram, do we draw both sheets of plywood, or do we need to? So problem 6 asks you to draw. So draw one diagram for each sheet of plywood. So I don't think I will, because I did answer quite a lot of questions here. There is another office hour, I believe, today. If not, we can schedule something, but I don't know how long the meeting will go, so I can't make any promises today. Yes, each sheet of plywood is 12 kilograms. I'm not going to hold an office hour today because I don't know when I'll get out of my meeting, and because I managed to answer people's questions now. I did hold 2 hours of office hours yesterday, but I only got 3 people that showed up. So, keep that in mind. Also, if you do still need help, you can, there is the physics club was holding tutoring sections, basically, via the email that I sent out. Sorry, via the announcement. There's more resources to you if you need them. And again, like if you urgently need help, feel free to email somebody. There's no guarantees that you'll get email somebody to schedule something. There's no guarantees you'll get an answer back, but it's something, right? Or ask or talk to your classmates as well. All right, I'm going to end it there because I do have to run to a meeting. Shoot me an email if you want to set up something, though later. I don't know when I'll get to it, and we'll see. So I will try to post the lecture today. I hope that the first half got recorded because my screen crashed, or my computer crashed. So yeah, today's a bit of a mess. If you're still confused by the material, go check the book. I know today was rough because of the crash and all that. Anyway, take care, and I will see you guys on Monday.